In Sleman, Yogyakarta, amidst vibrant rows of chili plants, farmers are confronting a critical challenge: the climate crisis. While agriculture sustains our food security, it also contributes to greenhouse gas emissions. But could chili farming become climate-friendly, even carbon-neutral? Join us as we explore innovations and nature-based solutions transforming chili agriculture in Sleman for the future of food and of our planet. Agriculture feeds the world, yet it accounts for nearly a quarter of global greenhouse gas emissions. In Sleman, Yogyakarta, chili farming sustains both livelihoods and national supply, but at a climate cost. From fertilizers to tillage, everyday practices release powerful greenhouse gases. As Sleman grows into a chili production hub, climate-smart solutions are more vital than ever. Join us as we explore innovations and nature-based solutions transforming chili agriculture in Sleman for the future of food and of our planet. To achieve carbon neutrality in chili farming, Sleman is adopting a set of innovative, climate-smart practices. Plastic mulch is replaced with organic mulching from rice straw and plant residues. Biochar made from crop waste is added to enrich soil carbon and cut nitrogen losses. Farmers reduce synthetic fertilizers by half, replacing part of it with chicken manure. Drip irrigation boosts water efficiency and minimizes nutrient leaching. And crop rotation with legumes supports natural nitrogen fixation. Together, these actions lead the way toward greener, more resilient agriculture for farmers and for the planet. This project takes place on a 10-hectare chili farm located in Sleman Regency, Yogyakarta, Indonesia. Sleman is one of the country's key chili production areas, with year-round intensive farming. The main goal is to reduce greenhouse gas emissions from agricultural activities. At the same time, we aim to improve soil health through sustainable and climate-smart practices. Under the business-as-usual scenario, chili farming in Sleman relies heavily on synthetic fertilizers minus 200 kilograms of urea and 200 kilograms of NPK per hectare. This leads to a nitrogen input of 122 kilograms per hectare, contributing to nitrous oxide emissions. Using IPCC estimates, these emissions equal nearly 573 kilograms of CO equivalent per hectare. A footprint this size shows the urgent need for climate-smart alternatives in agriculture. In the project scenario, chili farming adopts more climate-friendly inputs. Urea is reduced by half, while chicken manure provides additional nutrients. NPK input remains, but the total nitrogen applied drops to just over 100 kilograms per hectare. To further improve soil health and carbon storage, Biochar is added, enhancing soil organic carbon through organic mulch and manure. With these adjustments, nitrous oxide emissions fall to 1.02 kilograms per hectare. When converted to CO equivalents, emissions are reduced to around 469 kilograms, significantly lower than the business-as-usual scenario. This demonstrates how smart input management and soil-enhancing practices can meaningfully reduce the carbon footprint of chili farming. This table highlights the emissions difference between the business-as-usual and project scenarios. Under BAU, nitrous oxide emissions reach over 570 kilograms of CO equivalents per hectare. In contrast, the project scenario reduces these emissions to about 469 kilograms, a drop of more than 100 kilograms. But the real impact comes from soil organic carbon sequestration through biochar and mulch, which removes up to 2,000 kilograms of CO per hectare. As a result, the net emission balance shifts dramatically, from a positive footprint under BAU to a negative 1.5 tons of CO equivalents per hectare. This shows that sustainable farming doesn't just reduce emissions, it can actually reverse them. The project scenario shows a powerful impact. Total emissions drop to minus 1,530 kilograms of CO equivalent per hectare per year, thanks to carbon sequestration from biochar and organic mulch. Now, imagine a farmer managing 10 hectares of chili fields. That's a total greenhouse gas reduction of 21 tons of CO equivalent per year. This means the farmer could potentially earn 21 carbon credits annually. Each credit represents 1 ton of CO avoided or removed, and can be traded in voluntary carbon markets, offering not just environmental benefits, but real economic opportunities for farmers. Indonesia's chili farming is facing serious sustainability challenges, especially due to high greenhouse gas emissions from fertilizer use and poor soil management. Sleman, a major chili production area, highlights both the problem and the potential for change. This case focuses on 10 hectares of farmland with high synthetic input dependency and low soil carbon levels. With the right innovations such as organic practices, better soil care, and reduced emissions, Sleman could lead the way to a more climate-friendly chili farming system. To reduce emissions in chili farming, a set of practical mitigation strategies is proposed. Plastic mulch is replaced with rice straw mulch, and urea fertilizer is cut by half, substituted with chicken manure. Biochar is applied at 5 tons per hectare to enhance soil health and carbon retention. A drip irrigation system is introduced to improve water efficiency, and crop rotation with legumes is adopted to enrich soil nitrogen naturally. These measures lead to a reduction of over 100 kilograms of CO equivalent per hectare from fertilizer use alone. Additionally, improved soil organic carbon contributes to 2 tons of CO equivalent sequestered annually. Overall, the total net climate benefit reaches to 0.1 tons of CO equivalent per hectare per year, demonstrating a feasible pathway toward low-emission chili production. Beyond reducing emissions, these climate-smart practices bring powerful co-benefits. They improve soil fertility through organic matter enrichment, which boosts productivity over time. Input costs are reduced by minimizing synthetic fertilizer use and maximizing local resources like farm waste. Water is conserved with efficient drip irrigation, crucial in areas facing drought risk. And most importantly, these measures promote a circular economy, turning waste into valuable inputs, closing nutrient loops, and enhancing sustainability in the long run. This initiative presents a replicable model that can be adapted to other regions facing similar challenges. By integrating climate-smart practices, it contributes to building food systems that are more resilient to climate change. Most importantly, it empowers local farmers, equipping them with sustainable tools and knowledge to secure their livelihoods while protecting the environment.